Number 32 kind of brings up some interesting things that most books don't have you look at, in connection with these linear combination problems. If I want to try to solve this equation, what I want to do is get the x's or the y's to cancel out. But look at how large these numbers are. One thing you might notice is you might think, there's probably some numbers that divide into, like on that top equation, all of those numbers. I mean, okay, here's one way I could solve this. I could say multiply the top equation by 15 and the bottom equation by 24, and we could cancel our x's out, but wouldn't those numbers be huge? So that gave us some problems here where we could think about, maybe think a little bit outside the box about how we could solve these. In the previous problems I've worked, we always multiplied through an equation by a certain number. I'm going to multiply through by a number here, but I'm going to, instead of it being a whole number, I'm going to multiply by a fraction because I want you to think about this. 24 and 56 and 72 are all divisible by 8. So I can say I'm going to divide 8 out of all of them, but dividing by 8 is the same thing as multiplying by 1 over 8. So I'm still going to multiply everything. I'm just going to say I'm going to do it by 1 over 8 because that's the same thing as dividing by 8. I'm just kind of mincing words here, if you will. That top equation, if I divide an 8 out, 24 divided by 8 would be 3x. 56 divided by 8 would be 7y, but it'd be a minus 7y. And 72 divided by 8 would be 9. Now, that bottom equation, I could do something similar with it. I could divide both of them, like this. Or, now I could even combine this equation, 3x minus 7y is 9, with the second equation, which is what I did in class. But I want to go ahead on the video and just show you just something interesting that happens here. Aren't 15, 35, and 45 all divisible by 5? So let's divide by 5, but instead of saying I'm dividing by 5, I'm going to say I'm multiplying by a fifth, just so I can stick with the whole idea that I'm multiplying each of these equations through by something. I'm going to think of it as divide by 5, though. Negative 15x divided by 5 would be negative 3x. 35y divided by 5 would be a positive 7y. And negative 45 divided by 5 would be negative 9. Okay, so now if I add all these together, let's see what I get. Because it looks like some stuff's going to cancel out. I really care that a variable cancels out. And I see that 3x minus 3x would be 0. Or they cancel out. I'm going to write the 0 this time because I'm going to show you what else happens. Negative 7y and positive 7y, they would also cancel out. Or when we say they cancel out, what they're really doing is they're adding up to 0. So on the left side, I have 0 plus 0, which is 0. Now on the right side, what is 9 plus negative 9 or 9 minus 9? It's the same thing, no matter how I say it or think of it. It's 0. When is 0 equal to 0? Always 0 is equal to 0, right? That means no matter what x I pick to put in this equation, I can find a y that goes with it and it'll be a solution. This is always true, therefore, this is one of those that has infinite solutions because no matter what I try to plug in, basically at the very end, there's nothing to plug in. This equation is always going to be true if I pick an x on the line and the y that goes with it on the line. So this is infinite solutions. When we have infinite solutions, that means every single point on the line, because this is two of the same line, and really is what's happening here. These are the same line. They're just disguised. If I multiplied the bottom one by a negative 1, I'd have exactly what's on that, like that red equation there. If I multiplied it by a negative 1, then I would see that it's exactly the same thing as the blue equation that's listed here and here. Okay. So there are infinite solutions, and when we have infinite solutions, we call this a dependent system. It has infinite solutions because these two lines, when you graphed them, would graph right on top of each other. So this is, if you're solving algebraically and you get something that's always true, this means that it's two of the same line. So every point on the line is a solution, and there are infinite points on a line, therefore there are infinite solutions. 34 has similar numbers, so we can think of it similarly, but I'm going to show you that something totally different happens. On problem number 34, you have the same kind of numbers going on. We have 24x minus 56y is 72. We worked this in class, and I totally messed it up because I got a sign wrong, so I'm redoing this video with the correct signs and being more careful here. 15x minus 35y is negative 45. These are all the same numbers that were in the previous problem. I could, get something to cancel out, but I kind of know already what can happen with this. I can multiply the top equation by 1 over 8, which is the same thing as dividing by 8. I just noticed that divides into everything. So it's kind of just the same equation. I'm just reducing it a little bit. So if I divide the top equation by 8, which I'm going to write that as multiply by 1/8, just so we're still multiplying, that would be 3x minus 7y is 9. Now the second equation, which I'll write in blue, if I divide 5 out of each of those terms, or I multiply everything by a fifth, that's the same thing. That is a stray mark there, multiplying by a fifth. 15 divided by 5 would be 3x. Negative 35 divided by 5 would be negative 7y. And negative 45 divided by 5 would be negative 9. Let's see what happens here. Be careful that you don't think everything's going to cancel out. Be careful to do what the math tells you is there. Let's add this together. 3x and 3x is 6x. Negative 7y and negative 7y is negative 14y. None of my variables canceled out, did they? So I need to get some variables to cancel out. So let me do this. If I want, let's say I'm going to pick the x's to cancel out. Maybe I'm going to leave the top 3x positive and let me multiply the bottom equation by negative 1. That would change all the signs. So my top equation would stay the same. My second equation, which I'll write in blue, if I multiply everything by negative 1, that would be a negative 3x plus a 7y is a positive 9. And I kind of wonder if I've already messed something up here. This is negative 45. Okay, we'll just keep working. If you notice I've made a mistake, that may change the outcome of this, but I'm just going to kind of keep going. If I cancel this out, I get 3x minus 3x, if I add them together, is 0. Negative 7y and 7y is 0. And oh, but what's 9 plus 9? That's not 0, is it? It's 18. Okay, so I didn't mess up here. I was afraid I had for a minute. 0 plus 0 on the left side is 0, but on the right side I have 18. Is 0 ever equal to 18? No, not in our base 10 system, it's not. So this is never true, is it? Since it's never true, that means there are no solutions, because this is never going to work out for us, no matter what x we're trying to think of here. It's never true. There are no solutions. When do we have no solutions? It happens when we have two parallel lines, because they never cross. And if you remember, if you watched the first video that I recorded, and it's getting posted on Wednesday y'all are taking your SATs, PSATs. If I have two parallel lines, that system has a particular name, and that is an inconsistent system. It's inconsistent. Let me write that first. It's inconsistent with having any solutions, because they're never going to cross, so there's not going to be any solutions. So there are no solutions here. So when you get these nonsense statements where you have one number on one side and then another number on the other side, and you know they're not equal, that's when you have no solutions. That's what happens with algebra. And we have to interpret that result. That result is telling us this isn't working out. There aren't any solutions. And so what does that mean if there are two lines? It means that they're parallel.